All right. So a couple of reminders, the stopper lab reports are due today. And as always, you need to get those turned in by the end of the school day. So if you have them done in class today, you can just stack them over here on your way out or at some point during class. And if you don't have them quite done during first period today, you can try to get them done later throughout the day. Just make sure you get them turned in no later than 3:30. So at 3:30, I won't be taking them. I'll probably still be here, but I like to have this kind of a hard time. That gives you 15 minutes after last period. Actually, today it gives you 25 minutes. Plus I have a meeting at 3:30, so I have to go over to the other building and don't want to be late for that. So you need to get it turned in no later than that today. And then there is a new assignment. You can see number 3 on the agenda here. We've got some AP classroom things I want you to work on. We're in unit 4, and I'd like you to go to unit 4, section 1, and watch the 2 daily videos, as well as answer the topic questions for that. And since those are online assignments, those are due next time, but they're due before midnight that day. So I'll remind you again next time we meet, but that's your assignment tonight. Next time we meet, we're actually going to be doing some other things starting in class that day. So ideally, you would have that done before you come to class next time. So any questions about deadlines or due dates or anything? Yeah, Chris?
When are we gonna do the test correction?
We're gonna hopefully start those Friday. They're all graded, but I have 3 students that are still taking it today.
Are they on Access?
Yeah, I finished grading them Monday night and I put them on Access in the comments. I didn't, yeah, so they're in the comments. I put them on sometime yesterday.
Okay.
Is this on Access too, like the videos?
The videos are on AP Classroom. I can't transport them into Access. Oh, you mean the assignment?
Yeah.
Yes, the assignment is on Access. Yeah.
Some teachers like, oh.
I get it.
Yeah, so you have to go to AP Classroom to do it, but the assignment is listed in the assignments for Access, so you can see those details. All right, any other questions?
Yeah.
All right, so we're gonna go through a pretty healthy collection of slides today. There will be mixed in some example problems with some things you probably want to write down. We're gonna talk about the 3 key topics from this unit. We've already sort of dug into energy on Monday, but today we're gonna start expanding that into the concept of work and just briefly introduce power. And I was kind of mapping out the rest of the unit earlier today, and I'm pretty sure we'll be able to finish it by next Friday. Obviously, that doesn't give us any time for a test before ski week, so as I mentioned before, we're going to combine this unit on energy, work, and power with the unit 5, which will start right after ski week, and just have a single test on those 2 units. They're 2 of the shorter units and 2 of the easier units. They're probably the 2 easiest units this semester, and so we'll just combine those into one test. All right. So in your textbook, this content that we're covering this week and next is basically chapter 7 and chapter 8. So always my recommendation that you read through the chapters. I think they're well written. They are written by people who actually help make the AP exams. That's why this textbook was chosen, because the authors that made your textbook help make the exam, so they're going to explain things in a way that College Board wants you to understand them. They're going to give you practice problems and example problems like what you'll see on the exam. So that textbook is a really invaluable resource. But we're going to be talking about both chapter 7 and chapter 8 this week and next. Okay, so the key words to define today: work, energy, and power. We're going to define them in that order. And I think work is probably the one that often initially trips students up the most, because we use that word so often. I'm going to work, I'm going to get a workout, that was hard work, I have homework, all those kinds of things. But in none of those scenarios are we generally talking about what physics means when we say work. It's very specific when we talk about the physics definition. So in physics, the term work means an application of a force that causes an object to move over a distance. an application of a force that causes an object to move over a distance. And there has to be a causal relationship. So just because a force is applied and the object moves doesn't necessarily mean work was done. The force has to be, at least in part, causing that movement through a distance.
Yeah, now does that mean like it's force divided by distance or force times distance?
It's not a mathematical statement, it's a physical statement. So it's an application of a force causing an object to move a distance.
Okay.
Yeah, so this is not a mathematical statement, it's a statement of what happens.
Okay. Is the relationship like it's force times distance?
Yes,
Okay.
yeah, it's, I actually have all the equations here, we're gonna kind of discuss them, we're gonna break down that equation today. But yeah, that's what the equation ends up being, is force times distance. It's how the force and distance combine together. Now, another way to describe work is to say that it's also the transfer of energy from one sort of storage mode to another. So we talked about a number of examples of that Monday, like going from gravitational to kinetic energy, going from spring energy to kinetic energy, and we're going to look at a lot of different transitions from one storage mode to another throughout this week and next week. So that's another way you can define work. How energy, or what causes energy to go from one mode to another. So now that we've used the word energy to define work, we need to make sure we understand energy. And energy is the more nebulous concept because work has a very clear definition, even though it's probably different from what you have thought of in that word before. Energy is a little bit more broad to understand. And the first definition kind of cycles back to work. It is the ability to do work, specifically work as defined above. So it's not, again, the ability to do your homework necessarily, or to do a workout necessarily. Because if you, for instance, if you do a plank, you can hold a plank for 10 hours if you want. You've done no work because you didn't move. Okay? Now, you feel like you did work in the sense of the word that we've used, but unless you move your body over a distance, like doing push-ups, then you haven't done work. Where the plank may cause you to actually build a lot of muscular strength and get fit, it's not doing any work if you're not moving your body with that force over some distance. But we don't want to stop there, because then we're defining work based on energy and defining energy based on work, so it's kind of cyclical. We want to expand that a bit. So this next way to define that, using what we've described as work, we could say energy also is the ability to apply a force over a distance. So it takes energy to be able to exert that force, making an object move a distance. So now we're basing the definition of both terms on concepts from first semester, forces and distance or displacement. But we can take it a step further with energy, and we can define it so it's not quite as reliant on the meaning of the word work. Energy is also the ability to cause a change in the structure of a substance, or the configuration of a substance, or the motion of a substance. So we might be literally changing its structure by breaking down chemical bonds and reforming new ones, or reshaping its physical appearance. Or we might be just reconfiguring it, like moving it from a bottom shelf to a top shelf, or from a top shelf to a bottom shelf, just changing its arrangement within a system of objects. Or we might be actually changing its motion, speeding it up, slowing it down, turning its direction. All of those things would require energy because we're causing a change in those things. So now we've got a physics-based definition of the term work, and we've got a pretty fleshed out definition of what we mean when we use the word energy as an ability. And then the last word is power. And we're just going to define it today, and then we'll come back to it and revisit it more in the future next week, mainly the last day next week. It's the shortest, simplest concept, and you would generally only see one, maybe two multiple choice questions on the exam. It might show up as part of a sub point on an FRQ, It's just not a highly tested topic, so, and it's also pretty easy. So we will just spend a short amount of time on it, but you do need to know what it means. It is the rate that we do work, how fast or how slow we do the work. Another way to think about it is it's how much energy is consumed in a certain period of time. And when we say consumed, it's not destroyed, but it's used up in one form and converted to some other form. So that's why consumed is in parentheses, or quotations, I mean, because it's not used up in the sense that it's gone, it's just changed from one form to another. So we might consume electrical energy to create mechanical energy or thermal energy in an oven or something like that. Or both, like in a clothes dryer, where it's creating mechanical and thermal energy from the electricity.
Wait, so is energy almost like potential energy, like as an analogy, like potential energy is to kinetic energy as it is to work?
Say that again?
Like, is energy to work kind of like potential energy is to kinetic energy? Because it's like stored versus.
Well, energy can be kinetic, and so when we say kinetic energy, that still is energy. We're just describing that energy is wrapped up in the motion of the object.
Wait, but isn't it the ability to do something, not that it's directly doing? So wouldn't it be like a potential in the fact that it has the ability to, but it's not doing?
Well, ability to doesn't mean it's not doing it. I have the ability to do push-ups, and I might actually be doing them. Right? So energy is having the capacity to do it, and then when energy is being consumed or transformed, then it's actually doing these things. So I would be cautious getting wrapped up in trying to think about this saying, oh, it just has the potential to do these things. Because what we're trying to do is just wrap our brain around a concept that's nebulous, it's not physical and concrete. But it doesn't mean it just has the potential to. If I'm doing push-ups, I'm actually using energy and I'm doing work.
Yeah.
And so sometimes it is stored in the sense that we would call it potential energy, but sometimes it's actually being consumed or transformed from one storage mode to another.
But wouldn't that be work?
But well, we're gonna get there. Yeah. So if you do work, that requires energy.
Yeah.
And so we'll get there. It's a couple slides down the road. Yeah, a few more minutes. I almost said something that you wouldn't understand because it's Indonesian, but I used to say it all the time to my students in Indonesia.
What is it?
Sabar dulu mas.
Mm.
But yeah, unless you speak Indonesian, that doesn't really make sense.
I got
So,
you.
yeah.
What does it mean?
It means, please be patient, my child.
Oh,
Like literally.
got it.
Yeah.
Yeah.
All right, so, yeah, I used to say it to my son a lot too. He didn't care for that one. All right, so the law of conservation of energy. So we're gonna switch gears just a bit, and then we're gonna come back to these questions you're asking about. And like I said, energy is this nebulous thought, so it is kind of hard to separate from work, but that's a good thing, and we'll see why in a few minutes. So focusing on energy for a few more minutes, so before we talk about that connection. Energy can't be created or destroyed, it's just transformed. Now, it might be transformed into some type of storage mode that's useless to us, but it doesn't get lost from the universe. It just gets changed. And so, for instance, if I rub my hands together, I'm using chemical energy from my body to do mechanical energy, and then that's creating friction, and I'm losing that as thermal energy to the environment. I warm up my hands, but some of that heat and some of that sound is just lost to the environment around me, and there's really no way for me to regain that. Like it didn't disappear, it still exists. You hear the sound going and bumping into your eardrums, and I feel the heat, but it's not able for, I can't really capture it again and then transmit it to something else. So earlier I said like the electric energy could be converted to mechanical and thermal to dry your clothes. But some of that thermal heat also heats up the room where the dryer is at, and you can't really regain that. It's just sort of lost to the environment. It's not destroyed, but it could transfer or transform into a mode that's sort of irretrievable. And that idea of law of conservation of energy, that one and the work energy theorem, which is what I was mentioning that we're going to get to in a few minutes, those two concepts are basically the backbone of all the problem solving, is understanding that if we enclose a system, all the energy there has to have the same total sum the whole time. So even though a portion of that energy might be something I can't retrieve, we can still account for it. What would we call it? Yeah, dissipated energy, right? Might be thermal, might be sound, but generally speaking, we could just call it dissipated energy. So, but it still can be accounted for. So it didn't disappear, it didn't get destroyed. It just got converted into an unusable form potentially. All right, so we're gonna continue to break down some of these words we've already revisited. So this is starting to sort of be a summary and review here. One example of kinetic energy, which College Board abbreviates with capital K, a form of energy that is moving object, that all moving objects have. And so even defining the word energy as the ability to do something is almost limiting the concept, because it has the ability to do it and it might actually be doing it at the same time. So energy is one of those almost fundamental concepts that's hard to define. We had a similar conversation first semester and we talked about time. We know what time means, but it's almost hard to define without using the word time or using how we measure it, right? Energy is kind of the same way. It's a little bit difficult to put into words exactly because we know what it means and we know how to measure it, but it's such an abstract concept. We know it exists, we know how to measure it, but it's a little bit hard to put into words. So when we try to put it into words, we're always sort of limiting ourselves and putting ourselves in a box. And so even calling it the ability to do something can be limiting on what in reality it actually is. Another example, like we've talked about before, is different forms of potential energy, where it actually isn't causing motion for an object, or it isn't wrapped up in the motion of the object. And it will be based on the object's configuration. So if it's chemical potential energy, it's how those bonds are formed between the atoms. If it's gravitational, it's how those objects relate to the floor or the ground or whatever we're calling zero level, how far they could fall basically. If it's elastic potential energy, we're talking about the system's configuration and how much that springy object has been compressed or stretched. So it's basically how we've configured the objects within the system that tells us the potential energy that could become kinetic energy and actually do work. And then the last one, this is just another word, and your book, again, being written by people who help write the exam, use instead of dissipated energy, they tend to call it internal energy, which I think is less intuitive, but I want to make sure you're familiar with that term, because since they help write the test, not just these people, but since these people do help write the test, they could use this word, and I have seen this word show up in other College Board resources. So when you see this idea of internal energy, it's that energy that's stored in the random motions, those vibrations from sound waves, those increased thermal energy by the particles moving faster and gaining a higher temperature. So I would typically call it dissipated energy, because just in my brain that makes a little bit more sense, but you can also call it internal energy, and you'll see it occasionally referred to. I wouldn't say it's super common, but not something that you'll probably never see. So I want to make sure that you recognize this other term. So those are the three big categories. We covered them before. Movement, that's the energy that's wrapped up in an object's movement, the energy that's stored by an object's configuration, and then the energy that is internal to the system but random enough that we could say it's sort of lost from usability. It's not functional anymore, but it still exists. All right, so any questions about the three big picture concepts of energy types? Yeah.
Is there a way to like calculate all energy everywhere if there's like a definite amount?
I don't think it would be physically possible to calculate it everywhere, but that's what we're gonna think about things as systems. That's gonna be actually our lesson mostly on Friday.
Okay.
Is how we look at a system and how we define a system will help us make it manageable.
Okay.
So just trying to determine all the energy in the universe is just too grand of a proposition to try to accomplish.
But that's like hypothetically
Yeah.
real.
Yeah, hypothetically, there is a limited amount of energy and there is some value, we don't really know it, and because for a lot of reasons, it's impossible to determine. But theoretically, there is a fixed total value and it's just always changing.
Isn't that one of like the conflictions with like the Big Bang Theory? It's like,
Yeah, where did the energy come from? And yeah, so there's theories on how people try to explain that as well, so, but that is one of the arguments that people will bring up. Do you have a question, Don?
Is there like, might sound like a weird question, but is there like different types of energy, like not potential or kinetic or anything, but is there like cause there's like, you know, the opposite of matter, right? But is there like an opposite of energy?
I don't believe so. There's antimatter and dark matter and things like that, and there's, but I haven't heard any concept like that for energy personally. That doesn't mean that someone hasn't theorized somewhere about it and I just haven't seen it, but not that I'm aware of. All right, so let's talk about a couple of examples of how energy might transform. So the sun is giving off radiant energy, electromagnetic waves of energy, UV, infrared, visible light. If you know about electromagnetic radiations, you might know some of those types. And we know part of this green is the same exact words as you saw in the previous one, or two of Acts, remembering the law of conservation. But that radiant energy, those electromagnetic waves could be gathered from one form of energy by a solar panel and converted into electrical energy, transforming it from one type to another. And then that electrical energy could be used to operate a motor, which could be used to raise an object, giving it gravitational potential energy. And so the energy used to raise that object initially came from the sun. It's all just energy. And although we categorize energy as, oh, here it's kinetic and here it's thermal and here it's gravitational potential, and we try to categorize it, that's a human construct that we're trying to grasp this big concept. And energy is not like different when it's in motion and different when it's stored in a spring. It's just energy. Like I said, it's not something physical or tangible. But we know the effects of energy because of the work that gets done. And so if we know that we can witness these things, we know there's some concept, something that's not actually a physical, tangible thing, but something that helps us explain how these things relate. And so that's where we as humans categorize all these different types of energy, when it's all really just energy. And you can see down at the bottom, it says some energy might be changed into a form that isn't very useful. Doesn't mean it's not destroyed, so I mentioned that earlier as well. If we let go of this block, then that gravitational energy that came from the motor, which came from the solar panel, which came from the sun, all that process, if we then let go of it, it's just going to fall and turn that gravitational energy into kinetic, and it's just one more transformation. And then when it hits the ground, there's going to be heat, and there's going to be sound, and there's possibly sparks. Who knows what it hits and how big it is. There's going to be a release of that energy in forms that we probably can't ever re-grasp or regather and use again. Not because it was destroyed, but just because it became internal to the system, but dissipated in the sense that it's not usable. Another example, and this one actually shows up, this kind of a question actually shows up fairly frequently in different versions of tests and different types of test questions. If you have a ball, for instance, moving, what kind of energy does it have? Kinetic. And then if it collides with the spring, it's going to apply a force on the spring, and that spring is going to compress, but there's going to be a limit to its compression, and then eventually it's going to push back and accelerate the ball in the other direction. And this is just another example of a transformation of different energy. That ball's kinetic energy, since it is moving, is going to translate into what form of energy in the spring? Elastic potential. And as it compresses that spring, the spring is storing more and more and more elastic potential energy until it reaches its maximum compression. What's happening to the velocity of the ball during that time when it's compressing the spring?
Decreasing.
It's decreasing. So what's happening to its kinetic energy? It's decreasing. So as the kinetic energy decreases because the ball is slowing down, the elastic potential energy of the spring compressing is increasing because the displacement or length of its compression is getting bigger and bigger. And so we see the velocity decreasing as the kinetic energy of the ball decreases, and then we see the spring energy increasing as the spring gets compressed further and further. We can also recall Hooke's law, that this force that is exerted on the spring means that spring is going to then equal and opposite exert a force against the ball. So kind of in summary, the kinetic energy of the ball is transformed into potential energy of the spring. As the spring changes its configuration, that is a reversible one. In fact, in some forms, we talk about how Hooke's law, sometimes it'll show a negative in the equation to remind us that it's sort of a reversible and opposite force. If I apply a force on the spring in one direction, it's applying a force in the opposite direction. And so since the spring can apply a force, therefore it can actually do work and use that stored energy to redirect the ball, putting that stored energy back into the ball as kinetic. It's a reversible process. All right, now down at the bottom there's an interesting note. It's not huge, but it's going to come back for us on Friday. Remember, an object can't have potential energy. A system can have potential energy. So the ball and the spring are combining to store that energy in the spring. It's not just the spring itself. If the ball wasn't there, the spring couldn't compress. Right? There has to be, for a force to exist, there has to be two objects, right? That's part of the definition of how forces work. They come in pairs. So you need two objects to have a force. So for potential energy to be stored, there has to be two things. The bowling ball on the bottom shelf has potential energy because of the gravitational field of the Earth. So if the Earth wasn't there, the ball couldn't fall. All right, so you need the Earth and the ball for there to be gravitational potential energy. Atoms bonded together store chemical energy in the bonds, but you can't have a chemical bond unless you have at least two atoms. Right? So there has to be multiple objects for potential energy to exist. A single object could have kinetic energy, but to store energy, you need a system. All right, and then here is one other definition of energy. So if you don't like the ability to definitions, here's an alternate thought. It's a quantity used to measure the state of an object or system or its capacity to cause motion. So they're kind of just switching out the word ability for capacity, so it still feels pretty similar, but slightly different. And then work, which is what we're going to focus on here to finish up, is the transfer of energy from one system or object through mechanical processes, which require forces, to another system or object. So changing the energy from one type of storage to another, like the ball and the spring, like the solar energy in the solar panel and that whole example there. All right, so energy is this sort of nebulous quantity we try to measure so that we can understand the motion or configuration of an object or systems. And then work is a more tangible measure of what's getting done and how that energy gets transferred. And then power tells us how quickly it happens. So just revisiting power briefly, you all came up the stairs to get here this morning, right? So what force did you have to apply to get your body to the top? You had kinetic energy, but what force did you have to overcome to get you up the stairs? Yeah, your gravitational energy, or your gravitational force, or your weight, right? You had to carry your weight up the stairs. And even though the stairs are angled, you ended up going from ground level to second floor. So there's a certain vertical distance that you covered, right? So your body, you did work because you moved the weight of your body a distance that was, we're going to get into it more, a parallel to your force applied. So some of your force was upward and your body moved upward. All right. Some of you probably walked slowly up the stairs. Some of you might have jumped 2 by 2 up the stairs. Those of you that walked slowly, you had a longer amount of time, so you had a smaller power rating, but you did the same amount of work. Well, if you weigh the same as the other person you're comparing to. So if you have two people that weigh the same amount of work, but if one person walks and one person jogs, the first person who walked has a lower power rating because it took more time, and it's per time. Dividing by a large amount of time, you use smaller power. The person who ran up the stairs has a smaller time, so higher power rating. And we'll get to, let's actually do that right now before we go on to work in detail. Let's get to some units here. We'll get to a detailed power rating discussion later, but does anybody know what we measure power in? Watts. And watts, if you've seen like a 40-watt bulb, 60-watt bulb, or your microwave is 1,000 watts or whatever, that tells us how many joules per second that device uses. And so a watt for power, we'll just write that over here for reference. A watt, which we abbreviate capital W, is joules per second. Now, these forms of energy and work, I want to help derive the the units for these with these equations. So what's the unit for force? Newtons. What's the unit for displacement? Meters. And then cosine of an angle, that's just in degrees, it's an abstraction, so there's no units for that, right? I think we've mentioned it before, but it hasn't been formally part of our class until now. Anybody remember what a Newton times a meter gives us?
Oh, meters per second.
A joule, yeah. And it's not joule like a ruby or something like that. It's Joule. We'll see it in our notes soon, but it's named after a scientist. So remember, like a Newton is a kilogram meter per second squared. So we, instead of having to write all this mess, we just say Newton. So really a joule is a Newton. So that means it's a kilogram meter per second squared times meters. So a joule is kilogram meter squared per second squared. So instead of having to write all that, we just say joules. Okay. And then instead of having to divide it by seconds again, and then making it kilogram meters squared per seconds cubed, we just say it's a watt. Okay, so just to try to simplify things. But work is joules. All right, so how about the units here? What's mass? Kilograms. And then velocity? Meters per second, but it's squared. So meters squared per second squared, which is a Newton times what? A meter, right? Which makes this joules. See that? That making sense with the units? How about this one? Mass? Kilograms. Acceleration? Meters per second squared. Height or vertical distance? Meters. What's that? Newton meter, joules. Down here, what's this K value?
Oh, spring constant.
Spring constant. When you guys did that experiment, you did force on the Y, you did displacement on the X to get the slope as a spring constant. If it's force over displacement for your slope, what's the units for K? Let's stick with just newtons here to make it simpler for now.
Newtons per.
We could break it down that way though, yeah, so newtons per meter, right? That's how we found spring constant. And then X, the displacement, meters, but it's squared. So that makes a Newton meter, which is joules. So what do we measure work and energy in? Joules. And we can prove it using the equations. They all come out with the same units. All right, now that's going to carry over into these next concepts here. All right, so let's focus on work a little bit. Let's focus on this first concept and figure out why do we have this whole cosine theta. This is how the equations are on College Board's formula sheet right here. So that's, I'm trying to be consistent with that. They're all provided, but I want you to see them as you're going to see them on the handout. All right, so work. Work is done when a force acts parallel to the displacement. So this weightlifter, when he's got the weights over his head and he's now lifting them straight up and he's pushing his body more upright to get them straight up above his head, his force is upward, the displacement is upward, so he is doing work on the barbell. And when you do work, it requires energy. All right? There's all sort of energy transformations there, right? The chemical energy in his body, the kinetic energy of his body, the kinetic energy of the barbell, all kinds of kinetic energy transformations, but he is doing work on the barbell. Now we got the other guy on the right here pushing the lawnmower. He is also applying a force, and it is displacing the lawnmower, and therefore he's doing work on the lawnmower. But is he literally pushing the way that yellow arrow points?
No.
He's pushing at an angle, right?
Yeah.
So how would we figure out how much force is parallel to the direction of the lawnmower?
Triangle.
Yeah, we would have to use triangulation or trig, and if we think about this, he's pushing this way at some angle relative to the ground. We need the horizontal component. If this is the angle, what trig function do we find to get this adjacent side? Cosine. That's where the cosine comes from in the equation, because we need to know the force that is parallel to the displacement. So if it is at an angle, then we need to find that horizontal component that would be adjacent to the angle, generally speaking. Okay, so I'll talk a little bit later today about how you don't have to use cosine in certain problems, but that's the basic formula because of this relationship. So some of his force is pushing down, right? There's a horizontal component, but some of it is this downward component, right? Is that downward component helping to push the mower forward?
No.
No. So the downward component is not doing work on the lawnmower, only the horizontal component. So he's losing some of his effort, right? Some of the force he's applying is not helping him push the mower. He could be more efficient by lowering the handle, right? Getting it down further. But then he'd be uncomfortable because he'd be mowing the lawn like this, right? So there's a little bit of give and take on how easy it is to do it, but he would be more efficient at a lower angle because then more of the force he's pushing would be horizontal. All right. Now let's start to make the connection that you guys asked about before when I said we'll get to there in a few minutes. Here it is. So if we think about lifting a box and think about the work that's being done, we're lifting the box, meaning we are having to bear the weight of the box, right? And we know how to calculate weight, m times g. And we're lifting at a certain amount of height parallel to that. You know, we're lifting with the force upward. The box is moving upward. They're parallel in nature. And so I'm applying a weight force up or a force equal to the weight up a certain distance. So the work I would do to lift that box would just be the force I apply times the height, and the force has to equal the weight. So we could say the work being done is mass times g times h. I can find the work done with that equation. What does that remind you of, hopefully? mgh.
Yeah.
What does it remind you of that we've already talked about? Parker's pointing over here. It's the same equation. Here, what are we focused on? Work. Here, what are we focused on? Potential energy. The work we do creates the potential energy that we store on the object. Okay? Yeah.
Wait, wouldn't there be like a positive net force if you lift it up?
So if there's a positive net force, what does it mean?
Like it would accelerate up?
It would accelerate. So if I lift it initially, I'm going to have to accelerate it, right? Because I'll have to make it go from rest to movement. But then I could lift it at a constant velocity after that.
Yeah.
And so at that point, I'm not accelerating it any longer. I'm just pushing it forward with a constant force, a balanced force. And so there's going to be that instant at the beginning where we need a net force to accelerate it, and then we don't necessarily have to accelerate it beyond that.
Okay.
We could still be, and we would measure things a little bit different like we did, but this is just trying to help you see the overview of the connection here. Now the second part is, this is putting the box up on the top shelf, but what if I bring the box down? What's the force I apply to bring the box down?
And then it's still the weight for it.
Yeah, it still has to be the weight force. Which direction am I pushing?
Negative.
Oh wait, still pushing up.
Still pushing up, right? I'm not pushing the box down. If I lower the box, I'm still applying a force upward, but the box is moving downward, right? So work is not a vector, but force and displacement both are. And so we use signs with work, even though it's a scalar value, to describe the relationship of the force and the work. So when I lower the box down, I still have an upward force, but the box is moving down. So when the force and the displacement are opposite, but still parallel, I'm still doing work. We just call it negative work because we're trying to indicate the fact that that force, which is a vector, and that displacement, which is also a vector, are in opposites. They're facing opposite directions.
Would it be less work though?
It,
Cause like, you're going down with gravity.
you are going down with gravity, but you're slowing it so it's not in free fall, right? So
Yeah,
you're
but-
still having to supply the weight force to keep it from accelerating. So if I just drop it, it accelerates at g. But if I bring it down at a constant velocity, my force has to equal its weight.
Oh, that's the same thing when pushing.
Yeah,
If your force equaled its weight, then wouldn't it just stay still? Like when trying to push it up?
say that again?
If your force equaled its weight, then why wouldn't it just like not move?
So that kind of goes back to Aiden's question. Initially, I do have to apply a little bit more than its weight to get it going. But once it's moving, I can move it at a constant velocity,
Yeah.
and it's not accelerating anymore. So now the force I'm pushing with is the weight. They're balanced, it's just already in motion. So there is that moment at the beginning where I do need a net force to get it going. But then once I have it going, I don't necessarily have to accelerate it. I still could. If I wanted to pick it up fast, I could keep accelerating it, but
Yeah.
I wouldn't have to get the job done.
So I'm like, what explains like why it's like harder to lift something like say like a squat, for instance, like from the bottom up as opposed to vice versa?
Normally, when you're lifting it up, you are trying to keep a pretty steady velocity, right? You don't, well, it depends on the exercise, I guess, if you're trying to do like a jerk or something, but a lot of times you're trying to keep a pretty steady velocity. But then when you drop it, you don't necessarily, unless you're actually doing, like, if you want to get best out of your push-ups, you go up at a steady pace, or not push-ups, but bench press, and then you go back down at a steady pace. But most people just effort, drop. Effort, drop. And so constant velocity, letting it free fall. So they're not necessarily doing the same amount of work because they're providing less force. They're not keeping it from accelerating. Yeah. So when you lift something up, generally you're going at a more constant pace. And then when you drop it, sometimes you're literally dropping it, right? And it's just in free fall.
Okay, so it's explained by the different velocities.
Yeah.
of each-
When you're accelerating it, when you're not, when you're letting sort of gravity take over.
Okay.
Wait, but wouldn't you have to like counteract all that force at the bottom though, right? Like all the kinetic or
Yeah, but a lot of people, like with bench press, for instance, they're letting it kind of bounce off their chest a little bit, right? So then the chest is providing some of that force. Or if it's deadlift, they're letting it hit the ground and the ground's providing some of that force, so. Yeah, so if we start getting into the micro details of all the different elements, then we can start seeing some other types. Here, they're just trying to say, simply speaking, if we make it constant, that's great you're asking these questions because it's going to help you understand it, I think, deeper in the future. But here they're just trying to help you understand the mathematical relationship. All right, so if the work we do translates to the energy that we store, there must be something that connects those two, and this idea is what we call the work energy theorem. And most books define it this way, that the work done is the change in kinetic energy. That is true, but it doesn't have to be limited to kinetic energy. It could be the change in gravitational potential energy. It could be the change in elastic potential energy. It often is the change in kinetic energy, depending on the scenario. So that's what most books list. College Board lists it in the way you see it down here at the bottom, which I think is actually a better representation. They're just saying change of energy. They're not specifying it as potential or kinetic. They're just saying the change in energy is equal to the work. And work we can define as the force, and that's supposed to be two lines. It wouldn't change the font within this equation for some reason. So it looks like two L's, which is what it really is, but it's supposed to be like parallel lines, meaning that it's equal to the force parallel to the displacement. So that's what those two little lines are supposed to be representing. And because the force won't always be parallel, it might be at some other angle, we can extend that by saying, well, that would just be force times d times cosine of the angle. But if they're parallel, you don't have to worry about the cosine theta part. So as I mentioned before, the conservation of energy, and now as we're getting into this work energy theorem, these are the two parts of the backbone of how we are going to solve problems in this unit. Okay, we're just about done today, but anybody need more time on this slide? A couple more things to wrap it up. All right. So the rest of these slides are going to be hopefully helping you sort of process the math and make connections. I don't necessarily think you need to do a lot of note taking. I would just try to, you can whatever you want, and this is on Axis, so you can always go back and look at it, but I would focus in on just making sure you understand the concepts here, because it's more of an application of something we've learned before. So if a force is exerted parallel to the displacement, then work is done. And even though this block in the top picture is going up a ramp, if the force is directed up the ramp and the box is moving up the ramp, we don't even need the cosine theta part because they are exactly parallel. Okay? So just because the ramp is not parallel to the ground doesn't mean that we need to use cosine of that angle, because the force and the displacement are parallel. Okay? So we don't need the angle in that kind of a situation. Now, if we drew the free body diagram for this object though, maybe we wanted to find the friction force. Well, for friction force, we need to know the normal force, right? And the normal force is always related to the surface in what way?
Wait,
It's gonna be related to the weight, but more like geometrically, how is it related to the surface? Perpendicular. And so if this is perpendicular, how much is this force helping it go up the ramp? None. And so that normal force would have zero ability to do any work because it's not assisting in moving it up the ramp. So the work being done by that normal force, while it might be important to find the friction force, it isn't doing any work. That force isn't. And so what you're going to be doing in solving problems is drawing those free body diagrams, thinking about all the different forces and trying to identify which ones actually either are parallel to the motion or have a component that's parallel to the motion. And anything that's perpendicular, you could ignore.
So
Okay.
like the friction would be like something that's doing work, or
Friction would be, so if we're moving the box up, friction force would be directed which way?
the other way. So it'd be-
So it's doing negative work, right?
Okay.
So we're doing positive work up the ramp, friction would be doing negative work down the ramp, trying to slow us down or stop us. Okay. And then the weight force, weight's straight down, right?
Yeah.
So we could do components for that. It has a component that's parallel, but it would be pulling it down the hill too. So the weight, the X component of the weight would also be doing negative work. The Y component of the weight would have no relevance. All right. So work or no work, thinking about that whole idea of parallel versus perpendicular. A man holds out a heavy concrete block at arm's length for 10 minutes. Does that work or not, according to physics?
Nah, it's easy.
No, I don't think it's easy, but it doesn't sound easy to me, but it isn't work according to physics because there's no movement, there's no displacement. There has to be a displacement for it to count as work.
We're kind of exempt, but
Yeah, it's one of those things where, again, in physics, we're using the term work as something very specific, okay? A student pushes a car down the street.
That's work.
Yeah, the car is displaced, at least some of the force that they're applying is in line with the movement of the car, so that's work. A woman holds a box over her head while she's walking at a constant velocity.
No, not work.
It is not work, because which direction is the force she's applying?
Oh.
Up. Now, when she first started, she would have had to accelerate it forward, right? So at the very initial part, kind of like the question that you guys are asking, she would have to apply a little bit of forward force to get it going. But once she's at a constant velocity, objects in motion stay in motion. So that box is just going to keep on going. Her force is upward, the box's displacement is sideways. So that force is doing no work once she reaches that constant velocity.
Is the system doing work? It's just herself? If you just look at
yeah, she.
A system can't do work, but objects in a system can experience work. We'll get there Friday. Yeah, that's actually part of Friday's lesson. So, and that's why we have to define the system. So energy within the system is going to change and work affects that, but it would be a specific way. So that's Friday's lesson. All right. Oh, I gave you the answer, but I think you would know it. A child pulling a wagon along the sidewalk would be work. The wagon is moving, at least some component of that pulling force would be in line with movement, so that would be. All right. Now let's talk a little bit more about that angle when it does matter. So here, the object is actually moving along flat ground. It's not going up some kind of a ramp, but the force is at an angle, like maybe that wagon. Probably the handle of the wagon is at an angle, and as you're pulling it, you've got some vertical and some horizontal element to your pull, right? So this would be this case. The wagon is just moving across the ground flat, but your force is at an angle. So how do we find that work based on the force? Well, that's where the cosine theta comes in, because the total force we're applying, only part of it's doing work. Part of it's not actually changing the displacement of the wagon. Now, if you've ever pulled a wagon with little kids in it, you may have noticed that sometimes if your angle is too steep, you might actually lift the front of the wagon off the ground. And if you're doing that, then the vertical is doing work because you're displacing it vertically. But as long as it stays flat on the ground, only the horizontal component would be what we need to think about. And the cosine is what's going to give us that adjacent component. So let's quickly go through the math. This is all, I hope, kind of review. The cosine tells us the adjacent side, the horizontal side. Do we need to use the sine function for finding work? Why do we not need the sine function?
Oh, because that would be the verse.
Displacements.
Yeah, that is the vertical component, which will be perpendicular to the displacement. So that one is irrelevant. It doesn't mean the force doesn't exist. It just means it's not doing any work. Okay. All right. So the horizontal component is important, but the vertical component is not. And here they're just showing you, if you actually do the math and think through what it means, since that sine function is going to give us the perpendicular part of the force, it can't be doing any work. Overall, we are thinking about the forces being vectors. So even though work is not, if we think about those forces being vectors in their directions, we can still see only the horizontal force actually provides anything. We're just adding FD cosine theta to 0. And so it ends up just being FD cosine theta. And then kind of summing it up, on the left, we see positive work. And in this case, there's no angle, but we could say that is FD cosine of 0. What's the cosine of 0?
I mean, yeah.
1, right? Cosine of 0 is 1. So cosine of 0 degrees is 1, so it's just 1 times FD, right? If it's 30, now we need that horizontal component, so we would have FD cosine 30, which is about 0.87, so basically about 87% of the force is doing work here. The other 13-ish% is not really doing work, if we think about it that way. Both cases, though, the force and the displacement, at least the horizontal force and the displacement, are in the same direction, so those are positive work. And the negative work, this case, 180 degrees, displacement to the left, forces to the right. If we put 180 in there, we're going to still get FD mathematically, but they're opposite in direction, so we call it negative work. If it's at 150 degrees, again, the object's moving left, but the horizontal component of that force is to the right. That's also going to be negative work. It's still basically a 30-degree angle from the force to the horizontal, so it's still going to give us that 87% kind of mark. But that would be negative because of the direction of the force and displacement being opposite. And then if we think about that perpendicular component, or the normal force or something like that, if we put in the cosine of 90, what is cosine of 90? 0. So we do just get 0 when we plug it in. So you can always use the cosine of the angle, but if it's perfectly parallel, you can ignore that step, and if it's perpendicular, you can ignore the equation altogether because there's no work done. All right. Here is the last slide just to kind of show you with simple mental math, simple numbers. If we apply a 1 Newton force to move this block 1 meter, we can find the work done by plugging it into the equation. We don't need to use the cosine theta part here because they're perfectly parallel, but if we plug in cosine of 0, we still get 1 times 1 times 1, which is 1 Newton meter. And as we talked about earlier today, a Newton meter is what we call a joule, and here you can see the spelling. I mentioned it earlier, but you can see it now. And it's named after, I think it's James Joule, if I remember right, but anyway, that's where the name comes from. Most of them, like Newton from Isaac Newton and Joule from Mr. Joule, I think it's James. And then Watts, I forget his first name, but they all came from different scientists who contributed to the field. All right. Before we go on to there, any questions about what we covered today?
Yeah.
Yes.
So, wait, I'm so confused. Is work? So you have to actually be doing a force. So it's like it's like the acceleration then. Like you have to have a net force if you have work.
So there has to be a force applied, and so at some point there would have had to have been an acceleration if it was at rest.
Okay.
Okay. If it was already moving, well, probably there'd still have to be an acceleration at some point because you would have to be changing its motion to make a force applied. But the amount of work done isn't related to the acceleration directly, only the force would be. So once we know how much force it is, because you can apply forces in a balanced way, you know, if I lift the box with at constant velocity, it's a balanced force, the downward and net or upward or make a net of 0. So, but I am applying a force, and it is the opposite of gravitational acceleration. So there is still an acceleration in that way. It's just that the weight and my force balance each other. So overall, there's no net force.
Okay.
Yeah. So there will be an acceleration, but it won't necessarily be a net acceleration, except when we start the motion or stop the motion of something.
Okay. Yeah. That makes sense.
And some examples of network, like if you catch a ball, you know, it's moving towards you and you're bringing it to a stop, right? So you're applying a force over a distance to stop it from moving. Or if you forget to put your car in park and step out and it starts rolling down the hill and you run around behind it, it's trying to roll that way and you're pushing this way, right? So those would be examples of negative work where they're opposite. Anything else? Any other questions? Yeah, Chris?
So there's no work on projectiles like horizontally, because after you throw it, there's no more force on it, right?
Correct. Yeah. Anything else? All right, so we're gonna practice with an FRQ. I don't think we're quite ready yet since we're just starting energy. I'm not sure if FRQ and energy is the best use of time now, but anytime we can go back to forces and specifically systems like an Atwood machine, I think that is valuable. So I'm gonna give you, actually it was on the 2019, one of the versions from the 2019 exam. It's one of the released questions. I'm gonna give you one that asks you to think back on forces. We've talked a lot about forces today, and also kind of thinking about how it applies in a system like an Atwood machine, but slightly different from the last one that we did. So we worked on an Atwood machine a couple weeks ago. An example, today this one's a bit different because instead of two hanging, one's hanging and one's on a table. So it says that you're supposed to have 25 minutes to try to answer this question, but we only have about 20 minutes left. So I just want you to get as far as you can in 20 minutes, and then we'll discuss it at the beginning of class on Friday. I think that you're going to find parts of this question pretty easy and parts of this question challenging. So, which is typically how FRQ is possible.
I'm gonna say yes.
For this one, you won't actually. Okay. You're welcome.
Alright.
Friction.